Okay, hello, good afternoon, everyone. Yeah, it has been a very busy set of days, and we've not been able to go live, but at least to be able to have a session to to work on these things. Okay, so we are going to wait for a few others to join us, and then we can start. In the meantime, Caster, how are you? Mel, hi. Crispin, Rita, hello. How are you guys doing? Diana Mwanza, how are you? Diana Mwanza never misses a lesson. Hello, today people are winning airtime. I promise that 4 people win airtime. Okay, Dismas Chomba. How are you guys doing? Yeah, it's getting quite busy, but we'll make the most with the little time that we have. We'll make the most of the little time. Mwamusa, hello. Okay, but guys, okay, so the wangu fast. Yeah, like a week together would make a huge difference. Huge difference. You get? At least our meeting times are untouched. We should open quickly. All right, I think we can start. Who remembers Coulomb's law? Like, if I have a charge, this is the first question, and the first person to answer is going to get airtime. Okay, so I have charge 1, Q1, and I have Q2. Okay, and then these are separated by a distance, R. Okay, what would be the magnitude of the force of attraction or repulsion between these two charges? So, in short, I'm asking you to write Coulomb's law, like the equation that talks about Coulomb's law. So quickly, you can type that up as we're waiting for others to join us. So the fastest person to answer wins the airtime. And then, by the way, I'll be using the way things appear on my end, okay? The name or the comment that appears first on my phone here is what I choose. You understand? Okay, so Greenwell says KQ1 Q2 over R squared. Okay, so Greenwell wins the first airtime prize. Okay. Yeah, obviously you couldn't put magnitude, whatever, because, I mean, we couldn't put modulus bars because people are trying to win. Okay, so this is going to be F is equal to K Q1 Q2 over R squared. Okay. All right. We move. We start handling the first question. So at least you guys remember Coulomb's law, okay? It says that the force of attraction or repulsion is directly proportional to the to the product of the charges, and inversely proportional to the square of the separation distance, R. Okay. Now, we've been given this question. It's very interesting. It's a very interesting question, and I hope you guys have done static equilibrium or gone through dynamics or vectors analytical method. I hope you guys have done that. So there's this question. Okay, so you can write it down. It's actually an exam question. It came in if I'm not mistaken, 2018. Yeah, but then we're going to alter it a bit. So there's this question. We have two charges that have the same mass and same charge. And then these two charges are connected to ropes, and they have the same charge. Now, if these charges have the same charge, do you expect them to attract or repel? No airtime for this one. Do you expect them to attract or repel if they have the same charges? So I'm going to have charge 1. I'm going to have charge 2. Now, there will be no need of saying Q1, Q2, because these charges and the masses are the same. So I'll just say Q and I'll just say Q. Yes, if the charges are the same, are they going to attract or repel? Okay, they are going to repel. Yes, it makes sense. It makes sense. And then here is an axis that has been provided. Okay, this is like our normal. And then all angles will be read with respect to this axis that has been provided. This angle has been said to be theta. This angle has been said to be theta. And it makes sense. If the charges are the same, it means the force of repulsion that each will exert on the other or experience as a result of the other will be the same. Okay. So here, then they tell us the length of this rope is going to be L. Then they say derive an expression for Q in terms of theta, L, M, G, and K. Okay. So guys, I can question. Okay. The last time this question came, it was carrying 8 marks. 8 marks. I don't know if you guys can see this. Let me try showing you the question. Okay. So this is the question. I don't know if this is visible. So this is the question, okay? You can see charge Q with a mass of M. The distance, the length of the rope is L. Each has an angle theta. Then they're asking you to derive an expression for Q, and the first part has 8 marks, okay? So this derivation is very important, and it is going to put our understanding of Coulomb's law to the real test, okay? So pointers. Now, these are not going in, neither are they going out. Each will just be where it is. Like each will just be moving. And I mean rather, each will not be moving. And if each item is not moving, we can say the system is at what? Okay? If these two things are not moving, like they are just where they are, we can say the whole system can be said to be at what? That's more leakage than you need. The whole system can be said to be at. The charges are the same, masses the same, angles the same. So the whole system can be said to be at equilibrium. Excellent. Okay. So these topics are connected with everything else. And if the whole system is at equilibrium, it means Q is also at equilibrium, Q is also at equilibrium. I can just choose to focus on one of these. You get? So pointers, the system is at equilibrium. Is at equilibrium. And if a system is at equilibrium, then sum of the forces in the X is going to be equal to 0, and sum of the forces in the Y is also going to be equal to 0. The third condition, if there's torque, we also say the sum of the torques is going to be 0. Okay, so that's the first pointer. Next pointer, these masses are connected by a rope. This is going to be mass M, mass M. Same letter, no subscripts, because it's the same mass. Okay? Because these masses are going to be on Earth, so we're going to have weight. So include weight pointing vertically downwards. Include weight pointing vertically downwards. Okay. Now, each of these masses is connected to this part by a rope. What is the only force that can exist in a rope? What do we call the only force that can exist in a rope? What is the name of the force that exists in a rope? What do we call the name of the force that exists in a rope? I want us to do this together, okay? So the force that exists in a rope is tension. And Tension with respect, can you guys type that up and finish it up? Tension with respect to each object should be blah, blah, blah. Tension with respect to each object should always be. Tension with respect to each object should always be. So we agree. We're going to have tension in this rope. We're also going to have tension in this rope. Now, tension with respect to each object should always be doing what? Should always be doing what? Tension with respect to each object should always do what? Tension. I want to have a job. Tension with respect to each object should always. Tension with respect to each object should always be pulling. Excellent. Okay. So tension is going to pull on Q. Tension is going to pull on Q as well. You understand? It depends on what you are focusing on. If you focus on Q, the tension will pull, the rope will pull on Q. You get? Later on, when you do moment of inertia, you'll find that tension with respect to this point as well will be pulling. You understand? So it depends on what you are focusing on. So include weight pointing vertically downwards. Then include tension in each rope. Okay. Include tension in each rope. Now, this tension is neither in the X nor in the Y axis. So let me just draw this properly. Oh, include tension in each rope. Then next, just focus on one charge, on one mass. Just focus on one mass or one charge and draw its free body diagram. Okay, so we're just going to focus on one object. And it's up to you to choose whether this Q or this Q, whichever. I'll go for this Q. Okay. So this whole thing is connected. And because the whole system is at equilibrium, it means each item is at equilibrium. This is going to be mass M that has a charge Q. They haven't told us whether the charge is positive or negative, but it doesn't matter. All we know is the charge is the same, so there's going to be a repulsion force. The angle on each side was theta, so the angle for this side is just going to be theta. Tension in each rope should always be pulling, so this is going to be T. This object is on F, so I'm going to include weight pointing vertically downwards, mg. Okay. Now, let's go back to this diagram. Because the charges are the same, you guys said there's going to be a repulsion force. You understand? Q is repelling this Q, like it is, this Q wants to force this Q to move this side. And this Q wants to force this Q to move this side. You understand? So this Q is actually experiencing a repulsion force. Okay, so the repulsion force is going to be in this direction. This other Q is also experiencing a repulsion force in this direction. And the magnitude of the repulsion force is the same. You get? Because we've chosen to focus on this mass, with the repulsion force on our free body diagram will point to the left-hand side. Okay, this stuff is so easy. So the repulsion force is going to be included this side. And we're going to assume the repulsion force is along the x-axis. So I'll call this F repulsion. F-R-E-P. Okay. Now, what do you think we do to the T so that we can sum up the forces in the X and in the Y? Because the X is neither in the X nor in the Y. What should we do to the tension? What should we do to the tension? And if you look at this question properly, it reminds me of circular motion, banked motion, or conical pendulum. What should we do to the T? What should we do to the T? Resolve T into its components. Excellent. Okay. So T is going to have two components. One component will be in this direction. One component is going to be in this direction. And if this is theta, this is also going to be theta. You see that? And then, how do we know which component is going to have cos? Who remembers? how do we know which component is going to have cos? So you're going to get airtime for answering this one. How do you know which component will have cos? What mnemonic did we use? What mnemonic did we use? How do you know what component is going to have cos? What mnemonic did we use? What mnemonic did we use in the dynamics document? The one with an angle. Not really, not really. Put it the way that it was, at least, so that the quantum, So the component that is cut by the angle is the one that carries cos. The component that is cut by the angle is the one that carries cos. Okay. So, who was the first person to comment this? Miriam is just said the one with an angle. And then Caster says the one cut by the angle. Okay, and I can only choose one. I can only choose one. I can only choose one. Anyway, Caster is most correct because he phrased it the way we phrased it in the quantum document, in all fairness. Okay, so the component that is cut by the angle is the one that carries cos. Okay. So this is going to be t, because this is the component carrying cos, this is going to be t cos theta. This other one is going to be t sine theta. Okay. Now, so let me draw this without this t appearing. So the forces that are going to act on this are going to be, this is going to be t cos theta, this is going to be mg, this is going to be t sine theta, and then this is going to be F, force due to the repulsion force. Okay, the force due to the repulsion. Now, you remember Coulomb's law. Coulomb's law says force of attraction or repulsion is directly proportional to the product of the charges. So that is going to be, ideally it should be Q1, Q2, you can put them in modulus bars if you only want the resultant, divided by r squared. R squared is the separation distance from here up to there. You understand? R squared is the separation distance. Q1 is the first charge, Q2 is the second charge. Now, they haven't labeled any of these as Q1 or Q2. So Q1 will just be Q, Q2 will just be Q. Okay. So, F rep, force of repulsion, is going to be K, where I'm supposed to have Q1 here, I'll just put Q, times the other Q, divided by R squared. R squared is a force, is a distance of separation between the two. R squared is a distance of separation between the two. Now, let's look at this properly. R squared is this total distance. But if you look at this total distance properly, because the charges are equal and the masses are equal, it means the distance from here to there, this distance, this one that I've shaded, is equal to this distance from here to there. Like the two distances are equal. It's like basically this is going to be half of the separation distance. This is going to be half of the separation distance. You understand? So I would label this separation distance, I'll label it x. This x is from here up to there, just this distance. And if you look at this properly, we are actually forming a right-angled triangle. So this is the distance x. Let me just draw the right-angled triangle separately. This is our distance x. We've been told this is theta. We've been told the length of the rope is L. Okay, we are trying to make x a subject of the formula. What trigonometric ratio can we use? Basically, what is x going to be in terms of L and theta and an appropriate ratio? What is x going to be here? In terms of L and theta, what is x going to be? Quickly, use trigonometry there. So Katoa, blah, blah, blah. I'll give you a clue. We don't have the adjacent. We don't have the adjacent. All we have is the opposite and the hypotenuse. Write the full expression. Try and write the full expression. Try and write the full expression. Try and write the full expression. L sine theta. Excellent. Because if you use SOHCAHTOA, we're going to say x is equal to 10. Then this is going to be L. We are going to use sine because we have what? Opposite and hypotenuse, sine theta. So x is going to be replaced with L sine theta. We understand. So this formula, L sine theta. Yeah. So this formula, the original formula has r squared here. R squared. And I can say, okay, the distance from here to here is equal to the distance from here up to there. You understand? This distance from here to here, we have found it to be what? To be L sine theta. The distance from here up to here is also going to be L sine theta. You understand? So the total distance from here up to here is what we get by adding these. What is L sine theta plus L sine theta? From here to here, this is L sine theta. Again, from here to here, this is L sine theta. What is the total distance if we add these two L sine thetas? What is the total distance? What is the total distance? If we add the L sine thetas, if we add them, what is the total distance from where this charge is up to where the other charge is? The total distance, excellent, is going to be 2L sine theta. L sine theta plus L sine theta is going to be 2L sine theta. In short, it's like R is actually 2L sine theta. I hope you guys are not confused. Okay, so let me just quickly go back. The distance from one charge to the other, the total distance is going to be r. Okay? Now, we found that r can actually be divided into two parts. You get? The first part is going to be x. The other part is also going to be x. Okay? Then we draw a right-angled triangle for x. We're trying to make x a subject of a formula. We know this is L and we know the angle is theta. Because we don't have adjacent, we're going to use sine. And for sine, we get x is equal to L sine theta. Now, this L sine theta is only representing half of the total distance. Okay? So a full distance, we can either add the L sine thetas or we can multiply each L sine theta by 2. And we end up saying that the total distance from where this charge is up to the other charge is going to be 2L sine theta. Now, 2L sine theta is representing r. You understand? 2L sine theta is representing r. Okay. So, where we have r squared, we know each r is going to be 2L sine theta. I need to be careful in plugging in. You understand? So let me just simplify this expression. So where am I? Just a quick recap. We said the system is at equilibrium. Okay? This object is on Earth, so we include weight, mg. This object is experiencing a repulsion force. Here, we're going to call it F, REP. This is tension. And because this angle is theta, this tension can be resolved into two components. One component going up, one component going this side. You get? If this is theta, this is also going to be theta. This is going to be t cos theta. This is going to be t sine theta. You understand? For now, let me sum up the forces and then I'll replace FREP with what we derived. So we said the whole system is at equilibrium. So when the system is at equilibrium, all the forces should add up to what? When the system is at equilibrium, what should all the forces add up to? When the system is at equilibrium, what should all the forces add up to? They should add up to what, team? If the system is at equilibrium, what should all the forces add up to? Okay, all the forces should add up to 0. Okay, so we're going to have Now, it doesn't matter which one you take to be positive or which one you take to be negative, because the order doesn't really matter. But we're going to assume this is positive, this is negative. Up is positive, up is negative. The order doesn't really matter. Okay, so we're going to say t sine theta. Okay, because this is it will be negative because it's pointing the other direction. Minus FREP is equal to 0. So FREP can cross over. I can say t sine theta is equal to FREP. You see that? That is our first expression. Now we know FREP is, this mass was here, this mass was here, this is theta, this is theta, this is q, this is q. The separation distance from here to here is L sine theta. Separation distance again from here to here is also going to be L sine theta. The total distance is 2L sine theta. Okay, so FREP, this is going to be K Q times Q over R squared. You see that? So this is going to be K, Q times Q is going to give us Q squared divided by R. I'm going to replace each R. What did I say I replace each R with? Like, what is R equal to in this case? What is R equal to? What is R equal to? What is R equal to? We found it. Let me even give you leakage. What is R equal to? Nangulefo kutoba bati. What did we say R is equal to? Okay, so excellent, Boniface. So 2L sine theta. Good. So I'm going to put 2L sine theta. Now, remember that this R was squared, so I equally need to square the whole expression. So I'm going to say FREP is equal to K Q squared over, the 2 is going to be squared, I'm going to get 4. The L is going to be squared, I'm going to get L squared. The sine is going to be squared, I'm going to get sine squared theta. You understand? So wherever I'm going to have FREP, I'm going to replace that part with K Q squared over 4L squared sine squared theta. Okay. Yeah, so T sine theta is equal to FREP. Wherever there's FREP, I can replace with this. So I'm going to get T sine theta is equal to K Q squared over 4L squared sine squared theta. This is going to be our first expression. We've gotten this expression by summing up the forces in the X. And then we replace FREP with what we get after substituting into Coulomb's law. And we end up with this. And with an understanding that R is 2L sine theta. You understand how we got the 2L sine theta. The R is being squared, so even the 2L sine theta should be squared. I'll square the 2, I get 4. I'll square the L, I get L squared. I'll square the sine theta, I'll get sine squared theta. This gives me my first expression. This stuff is so easy. Almost no thinking. Next, let me sum up the forces in the Y. The two forces that we have in the Y are T cos theta and mg. And because the system is at equilibrium, I can equate them to 0, or their mass. I can add them and equate their masses to 0, and equate the forces to 0, or I can simply equate them to each other. It doesn't matter. So I'm going to say T cos theta minus mg is equal to 0. Okay, which just means T cos theta is equal to mg. This is going to be my second expression. Now, I don't know if you guys remember the question. I do not know if you guys remember the question. But we said they want you to find Q in terms of theta, K, M, G, L. They didn't mention T. You understand? So T can actually disappear. I have this expression that has T, and I have this other expression that has T. I can make T the subject of a formula in any one of them and replace into the other. So it's easy for me to make T a subject of a formula for equation 2. I'll just need to divide both sides by cos theta. Okay, so I'll divide this side by cos theta. I'll divide this side by cos theta. and I end up with t is equal to mg over cos theta. So wherever I have this t, I can replace it with mg over cos theta. Okay, let's go. Okay, where am I? So we have t sine theta is equal to k q squared over 4l squared sine squared theta. Okay, and then we find out that t can actually be substituted with mg over cos theta. So we do the substitution. So this whole t will be replaced with mg over cos theta. So this becomes mg over cos theta times sine theta. Careful, this sine theta that we found is actually a numerator, or it's as good as over 1. Everything is equal to k q squared over 4l squared sine squared theta. You see that? Now, this cos and this one can swap because they're multiplying each other, and multiplication is commutative. I want you guys to notice something. We're going to get mg over 1 times sine theta over cos theta is equal to k q squared over 4l squared sine squared theta. What is sine theta over cos theta? We did trig recently. What is sine theta over cos theta? What is sine theta over cos theta? What is sine theta over cos theta? Good. Sine theta over cos theta is tan theta. This stuff is so easy. We get mg tan theta is equal to k q squared over 4l squared sine squared theta. They want us to make q the subject of the formula. Okay? They want us to make q the subject of formula. So this should multiply that. I'll cross multiply. I'm going to get k q squared is equal to mg tan theta. Okay? And then multiply by what? 4l squared sine squared theta. To make q squared the subject, I'm going to divide each item by k. Okay? So divide by k, divide by k. So I end up with q squared is equal to mg tan theta. I'll write this over k. Okay? Okay, times 4l squared sine squared theta. You're going to understand why I have put a times sign here. Now, how can I make q the subject of a formula? What should I do? How can I make q the subject of the formula? What should I do? What should I do? How can I make q the subject of the formula? How can I make q the subject of a formula? What should I do? Mama, ndemi pero tu anguka. Na sange fya kosa na mpele fya anguka. Okay, so I'm going to square root both sides. Aye. So I'm going to square root this side, and I'm going to square root this side. Now, I want you guys to notice something. There are things here that have a square root, and there are things that do not have a square root. You get? 4 has a square root. L has a square root. Sine squared theta has a square root. But the things that don't have a square root are m, g, tan theta, and k. These don't have a root. These have. These don't. These have. You understand? You guys should know the property square root of a times b is as good as square root of a times square root of b. You get? So this root, the overall root, can be split so that the root is for 4l squared sine squared theta and for mg tan theta over k. This stuff is so easy, almost no thinking. So square rooting, we are going to get q is equal to, because after square rooting I'll just have q. Q is equal to square root of mg tan theta over k. You understand? Times square root of 4l squared sine squared theta. If you remember, we got 4l squared sine squared theta because we had 2l sine theta. You get? And we squared it. So this whole thing can be written as, q is equal to square root of mg tan theta over k times 4l squared sine squared theta can be written as square root of 2l sine theta squared. I don't know if you guys see this. If I expand 2l sine theta squared, I'm going to get 4l squared sine squared theta. You understand? You remember, this represented r, and when we squared r, we got that. Meaning, this square root and this square cancel out. I'll just be left with what's inside. Now, what's inside is not affected by the root, so it can be written in front. So we're going to have q is equal to what's inside the root here. We're going to have 2l sine theta, then multiply by, everything will be multiplied by root. We're going to have mg. I'll write it over k, because this k doesn't affect this theta that comes after tan. So I'll put these in brackets so that they seem to be separate. And then I'll write the tan theta afterwards. That is the equation that they wanted you to derive. Okay. Actually, the full question that they asked, I don't know if you guys can see this. They asked you to derive an expression in terms of q. I don't know. Is the phone able to focus here? Okay, good. So they ask us to show that q is equal to 2l sine theta square root of mg over k tan theta. And this question was carrying 8 marks. And this is exactly what we have done. 2l sine theta square root of mg over k tan theta. You get your 8 marks. Then the other question, which I will not do, it's straightforward. Find q if m is 10 grams. Obviously, you're supposed to convert grams to kilograms. L is 50 centimeters. Obviously, you should convert from centimeters to meters. And your theta is, this phone can't seem to focus. Yeah, your theta is 10 degrees. So you can plug everything in and you solve for q. Okay. This stuff is so easy. So easy. Okay, so I did not want this session to be extra long, so please watch this video. I would regard our sessions on static done. Okay, the only other thing we should now do is the Kirchhoff's laws. For those that have won airtime, text me. I don't know if it's 3 or 4 people, I can't remember, but I remember. Text me with your with the Facebook name that you use. My Facebook name is blah blah blah. Text me, I won the airtime. Only those 3. Okay. So we will have another session at night. If you haven't understood what we have done, please watch this video again. And please gun those laws I gave you in the group, the Kirchhoff's laws, so that when we start, we don't have to go through them. You understand? Okay, guys, we will meet again. The time will be communicated. Have a good day, take care, and I hope you guys are revising. Okay, I am going to repost term 1 notes. Quite a number say they can't download them, so network has been tripping here. I'll repost them. Yeah. All right, have a good day.